All right, to continue on with this example, so I'm going to go back a moment. I just want to talk about subscripts. So whenever we're using variables, we're going to very often use subscripts. If we're dealing with our initial quantities, we're going to use a subscript of either an I for initial, or a 0, which is, we're actually going to most often use the 0, also pronounced not. Now for our final variables, we can label it with an F or no subscript. So no subscript refers to the final instant. But if we have more than one important moment in our analysis, we can just use subscripts of 0, 1, 2, and so on and so forth to how many moments are important to us. Right? So here, of course, in this diagram, I don't use that notation. I use I and F instead of zeros and nothings. And the reason why we're going to use the zeros and nothings is just because that's the way they use it on the AP formula sheet. Okay. So we can describe Ricky's change in position, also known as displacement, by calculating delta x. Right? So this delta is used to mean a change in a quantity, so delta x is change in position. Just kind of to note, kind of be a little bit pedantic about this, delta x is a single symbol. Delta is not something algebraic, so you can't divide out deltas or something like that. Delta x is one symbol. So in calculating this delta x, so it's going to be our final position minus our initial position. So our final position is 150 feet, our initial is 50 feet, so that leaves us with 100 feet. Right? So 100 feet is actually the magnitude of our displacement. Right? I say magnitude because I didn't indicate direction. So if we're indicating direction here, in this calculation, my final answer was positive, and since I'm called to the right being positive, delta x is 150 feet in the east direction. Okay, so a lot of times it's going to be kind of, I don't want to say easier, but it'll be a more clear answer if we revert back to just kind of a general statement of which way is positive rather than relying on your positive and negatives. Also note, if you see here, sometimes I refer to delta x in bold. A lot of times in text, so if you look at your textbook, if we're dealing with the vector quantity, it's going to be in bold print. Otherwise, it will often be, there'll be some, like a little bit of an arrow on top of that symbol, meaning that it's a vector quantity. So just kind of an FYI, we can, use this negative sign to indicate direction. So if we had walked to the intersection from where he is now, right, he would walk a negative 50 feet, right, or 50 feet westward. So I also just want to mention we're going to be dealing with changes in time very often. So change in time is symbolized by delta t, so it's our final time minus our initial time. Generally, our initial time is going to be 0, just because it's kind of a simple place to count our initial time as being 0. So if you look on the AP formula sheet, delta t is not really used there, whereas just t is, because we have our final time minus 0, it's just our final time, so just t. So kind of as a question to think about is, well, we know displacement can have a negative value. Can a time interval ever be negative? So take a moment, think about that. All right, so time intervals can never be negative because time always moves forward. So our final time is always going to be larger than our initial time, so it can't be negative. So that is not to say that scalar quantities can't be negative. They can be, just not time. Time can always has to be positive. All right. So here's an example. How long a ride? So Lucy's enjoying a bicycle ride on a country road that runs east-west past a water tower. So first things, we're supposed to define a coordinate system so that increasing x is moving east. So we're told which way to call positive here. So that means in our final answer, we're more than welcome to state our answer in positive or negative in terms of direction. So at noon, Lucy is 3 miles east of the water tower. Half an hour later, she is 2 miles west of the water tower. What is her displacement during this half hour? So hopefully, looking at this problem, you might think, well, let's define our origin to be the water tower. That seems to be a nice location to call R0. So that means that Lucy's initial position, x naught, is 3 miles, and her final position, x, is negative 2 miles, using the positive and negative signs for east and west, respectively. I also labeled here the time difference, though it's not really useful, but our initial time is 12 o'clock, our final time is 12:30. So if we wrote delta t, we could write 30 minutes. But long story short, let's look at our displacement. Delta x is our final position minus our initial position, so it's a negative 2 miles minus our positive 3 miles. So be careful with your negative signs. And that leaves us a total of negative 5 miles. So in other words, that's 5 miles west of the tower. So a question for you guys to pause in just a moment. So Julian here starts at a positive position along the x-axis. He undergoes then a negative displacement. Is his final position positive, negative, or could it be either positive or negative? So ponder it a moment, pause if you will, and then check back. So hopefully you thought about it and came up with the answer C. Their final position could be either positive or negative. Right, so kind of an example of this. So negative displacement means we're say moving in the negative direction, right? So if Julian moved, let's say, a negative 3 meters, but he started at a location of positive 5, that means he's at a location at positive 2 meters in the end. Whereas if he started at, let's say, 2 meters and then moved a negative 3 meters, he'd be at negative 1 meters. So in both those instances, we have a negative displacement. But it could have been either positive or negative depending on Julian's initial position. So now I just want to talk about uniform motion. This word uniform means the same, and we're going to be using it a lot in physics. So we're talking about uniform motion. What we mean is motion along a straight line at a constant speed. That's what I mean now. Later on we'll be dealing with uniform circular motion, so that's going to be an object moving in a circle at a constant speed, but we'll leave that for later. So when we're dealing with uniform motion, if we were to draw a diagram, so we're thinking about maybe the separate frames, the successive frames of motion, they're going to be equally spaced apart, right? Because whatever object we're dealing with is going the same amount of distance per unit time. Okay? So our object's displacement is delta x between these successive time frames. Objects can be moving at non-uniform speeds. In this case, that would mean that the object's accelerating. And we're going to worry about acceleration in the next lesson. So a formula here for average speed. So in our case, for uniform motion, our average speed is the speed because it's the same speed all the time. But anyway, average speed is going to be the distance traveled in a given time interval divided by the time interval itself. Right? So speed is a scalar quantity. It has no directions. Right? So if you're driving your car, when you look at your speedometer, it's your speedometer. It's telling you what speed you're going. It doesn't indicate direction, just how fast you're going. So another quantity you're going to be looking at is called velocity. Right? We use the symbol of V to symbolize velocity. In fact, we want to actually bold that symbol because velocity is a vector quantity. Right? So to fully describe the motion of an object, right, if you're driving a car, you can say you're moving at, let's say, 30 miles per hour, right? But to fully describe the motion, you want to say what direction you're going. That helps us be a lot more precise. So velocity is going to help us do that. So to calculate average velocity, what you do is you take the displacement of whatever the object is divided by the time interval you're analyzing. Right? So kind of in a formula-wise, we have V is equal to delta x over delta t. Where delta x here symbolizes displacement, and delta t is the time interval. So kind of an example of bicycles traveling at the same speed but different velocities would be both of them traveling at, let's say, 2 meters per second, one in the forward direction and the other one perhaps in the backward direction. Right? So they have the same speed, they have different velocities because they're going in different directions. So just note, speed's always going to be a positive number. Sometimes speed is going to be the magnitude of velocity, but velocity can be either positive or negative. It always has to indicate direction. We're also going to be dealing with instantaneous velocity from very often in this class, but it's basically the velocity at a split moment in time, and that's what this math here says. It says that velocity, the instantaneous velocity is going to be the limit as our time interval shrinks to 0 of this relationship of displacement over time. So we're not really going to be dealing with limits in this class. But if you're looking at the AP formula sheet, which I know you guys don't have yet, you can Google it online if you want to. But this delta excuse me. So this, whatever, when you see velocity on that formula sheet, it's referring to instantaneous velocity. Especially in the formulas we'll be dealing with in the next lesson, that's going to be instantaneous velocity. Right. So kind of a quick example here in terms of finding a speed. So albatrosses, they're speed birds. Well, I say seabirds, but they're also speed birds that spend most of their lives flying over the ocean looking for food. Right. So with the stiff tailwind, these birds can fly at high speeds. So satellite data on one of these birds shows that it is a location of 60 miles east of its roost at 3 p.m. and then at 3:20 p.m. it's 86 miles east of its roost. So what is the average velocity? So kind of writing what we know. So the first thing I'm going to do is define eastward as being positive. That way I don't have to keep writing east or west. Positive value is eastward. So our time interval here is 20 minutes since we're dealing with 3 p.m. to 3:20 p.m. So delta t is 20 minutes. So at our initial time of 0, we're at a location of 60 miles, so that's x naught. At our final time, so after that 20 minutes, we're at a position of 86 miles. Right, so that's my x and x naught. So now we're dealing with what's the average velocity. So our velocity is displacement over time. Our displacement is our final position minus our initial position, which is a value of 26 miles. We divide by our time interval of 20 minutes, because it's traveled these 26 miles in that 20 minutes, and we get a value of 1.3 miles per minute. Right? So, and if we want to be a little bit more general in our statement, it's 1.3 miles per minute eastwards. So now if you notice though, the title of my slide is actually kind of inappropriate because I say what's the speed of the seabird. I should really say finding the velocity of a seabird because we are indicating direction because the problem asks for the average velocity. And finally, I just want to kind of mention, with units we see here we have this per and meters per second, right? So the units for speed and velocity are a unit of distance, so that can be feet, meters, miles, depending on whatever we're dealing with, divided by some unit of time, seconds, hour, milliseconds, who knows. The standard unit used in physics is meters per second, right? That's our SI unit. So this word per here just really helps us kind of think about what it really means to have a velocity, to have a certain meters per second. So, for example, 23 meters per second means that every 1 second we're traveling 23 meters. Right? That's really what it means. So I do recommend that whenever you're dealing with the funky unit, especially when we get to acceleration, kind of think about what the unit means. So with velocity, it's the amount we traveled per unit time. So I don't know. I find it really interesting to think about. It helps me understand what the quantity really means.